Hi everybody, welcome to another video in Precalculus, section 8.4, Vectors. In simple terms, a vector is a quantity that have magnitude and direction. So we usually use an arrow to characterize a vector. So an arrow, of course, will have the length, and then the arrow at the arrowhead will indicate the direction. Right. So next we have three different things. First, we have a line. So a line PQ, usually we don't have the arrowhead here, but a line extended on both sides. Now, if we restrict it, we have the endpoint, then we have the line segment. So the line PQ, we just say PQ with no other notation is called a line PQ. We a line containing the point PQ that will extend both directions. If we write the line segment PQ, so we have P and Q are the endpoints of the line segment. And notation for the line segment is a line above PQ. And now we write a directed line segment P to Q. The notation will have an arrowhead above PQ. So that is three different quantity, and the vector is a directed line, and it's called the geometric vector. So usually the concept of a vector, of course, there's no one definition of a vector. A vector can be represented by different things. Geometrically, it will be by an arrow. Later on, we'll use components to represent a vector algebraically. But what we have is that a vector has a magnitude and a direction. Most importantly, it has no location. So what do I mean by that? Well, before I go to that part, the vector v whose magnitude is 0 is called the zero vector. By the way, the most important here is that the notation for vector. We can write PQ if there's two endpoints PQ, initial and final point. Then we use the arrowhead, the arrow on the top of it, to indicate a vector. If we represent a vector by one letter, that has to be boldface. If we cannot type the boldface, if we have to write it, we will write the vector V. This is the boldface V to distinguish between a vector V and a number V. This is the notation. It is the bold V. The notation for vector, we use the bold-faced letter to distinguish between the vector and the variable. Right, you see that in here. A vector V whose magnitude is 0. This is a number 0. The zero vector is the boldface. If we cannot type it like that, then we write so that is the zero vector, is the boldface 0 to distinguish the zero number and the zero vector. Of course, the zero number, it is a quantity, and the 0 here we have the magnitude equal to 0, and of course it has no direction if it is equal to 0. So zero vector has no direction. So up to this point, we say that a vector has magnitude and direction, and we also say there's no location. What I mean by that is, if we have a vector V like this, as long as it has the same magnitude, meaning the same length, and it points in the same direction, then they're equal. The location doesn't matter. This vector and that vector will be the same because have the same magnitude and the same direction. So they are the same. Right? Location doesn't matter. And the first part of the section here, we represent vector as a geometric sense. Later on, we'll worry about that in the algebraic sense. Right. Now, how do we add vectors? Adding vector, there will be two ways to do that. It's called the triangle method and the parallelogram method. So let's say we have the vector v. So that is vector v and vector w. Right. Let's say we try to add this vector v and that vector w. Notice that this mentioned vector has no location, so you can move them around. So you can move vector v to here and move vector w there. So in the triangle method, or we sometimes refer to a head to tail. Or sometimes heel to toe. So think about this. We move the vector anywhere we want to. So move here. And we say the head of the first vector will be the tail of the second vector. So we go from this point to that point, follow vector v, and from that point to vector w. And initially we start here and we end up there. And the sum will be the initial point of the first vector and the final point of the second vector, where the head and tail, the head of the first vector is the tail end of the second vector. Right, so that is a head to tail method. So we put one vector here, and then we put the other vector. And when we do that, that is the sum of the two vectors. So that's one way to do that. The other is called a parallelogram. Once again, we can move the vector anywhere we want to. By the way, this is different representation. So we can move v and w when they have the same tail. In that case, the diagonal is going to be the sum of the two vectors. So either we use the diagonal of the parallelogram where they have the same tail end, the same tail, or we use the head to tail method, or the triangular method. Right. Next, vector addition. Vector addition is commutative, meaning v plus w is equal to w plus v. As you notice that all of this vector, I will use the boldface letter to represent vectors. So later on we will have numbers. We will not have the boldface. So v plus w is equal to w plus v. So commutative, meaning that you change the order of those in the sum. And then vector is also associative, meaning that we will change the parentheses. So u plus v plus w. Associative, meaning that we can add the first two or we can add the last two first. It doesn't matter. The order will stay the same. We just move the parentheses, and associative say that if we move the parentheses, the sum is still the same. Right. For any vector v, v plus vector 0 is the same thing. 0 plus vector v is equal to v itself. If any v is any vector, then negative v is the vector that has the same magnitude but opposite direction. So one point that way, the other point the other way. And when we subtract, if v and w are two vectors, the difference is defined as v subtract w is v plus the opposite of vector w. let's say up to this point, vector represent as a geometric in the geometric sense. Right. Scalar multiplication. The scalar is a number as opposed to a vector. So the scalar has no direction. It's only have a quantity in terms of a number or magnitude. Right. If alpha is a scalar, you see alpha now is the regular phase. It's not a mole phase. So we distinguish a number with a vector, which is the mole phase. By the way, you will see a lot of different notation for vector. You may see the vector v. We can see the vector v, and some say the v with the dot on the top, but I will not go that far. Usually I use the bold phase v here as opposed to the arrowhead. Right. So if alpha is a scalar, v is a vector, the scalar multiple alpha times v is defined as follows. If alpha is positive, alpha v is the vector whose magnitude is alpha times the magnitude of v. So pretty much we just alpha multiplied to the magnitude of v. So if it is bigger than 1, it will get bigger. If it is smaller than 1, it will get smaller. Alpha is negative, then we will multiply the magnitude, but because of the negative, it will go to the opposite direction of v. And if alpha is equal to 0 or vector v is equal to 0, then the product of the number v and the vector v is equal to a 0 vector, not a 0 number. Right. So a scalar times a vector is a vector. So that's why this is a vector 0. So we summarize as 0 numbers times v times vector v is 0 vector. Number 1 times vector v is the vector v. Negative 1 times vector v is negative vector v. The sum of alpha plus beta times vector v is alpha times vector v plus beta times vector v. So this is distribution, and this also distribution. And scalar multiplication is also associated. Right, so we have some example here. If we have the vector v is this much, then the 2 times vector v will be twice as long, but point in the same direction. As vector v, and negative v will point in the opposite direction as v. If we have negative 2, it will be that, but it will be twice as long. Right. Here we have some example here. Given the following vectors, we have u, v, z, and w. Find vector v subtract vector z. So first of all, vector v is 1, 2, 3, 4 to the right and 2 up. So that is vector v. Just put that somewhere in here. 2 to the right, 4 to the right and 2 up. So this is vector v. And then minus vector z. By definition, we can say v plus opposite of vector z. Vector z is 1, 2, 3, 4, and 5 up. Negative z is the vector pointing down 5 units. Alright, so I'm going to use the head to tail method or triangle method. Z is that direction, so z is the 5 unit long, but if it point down instead of up, this is negative z. And when we put them together, we start from v, this is v, and then negative z. We end up with this. So this is v minus z. be that vector. V minus Z. So that is V minus Z. Right, next, 2W plus U. Right, vector W is this. And we're going to have twice as long. So originally we have 1, 2, 3 to the right, and then 4 units down. So that is W. So 1, 2, 3 to the right, and 4 units down. So that is a W, right? Because it's pointing down. But this is 2 times W, so it will be twice long. That is a vector 2W. And then plus U. Vector U is this much. 1, 2, 3, 4, 5 to the right. And once again, I've used a head to tail method. If we use head to tail, then we just draw a vector V here. 1, 2, 3, 4, 5. And that is vector U. And this is 2W plus U. Of course, we can also use the parallelogram method, where we can move the vector U here, and we draw a parallelogram, and the diagonal will be the sum of the two vectors. Right, so once again, first we'll only study vectors in geometric sense, geometric aspect of it. Right, now once again, vector has magnitude and direction. Now we focus on the magnitude. The symbol 2 bar and vector V in between represent the magnitudes of V. Since V equal the length of directed line segment, the magnitude of V has the following properties. It is the length, so it cannot be negative. It has to be greater than or equal to 0. The magnitude is equal to 0 if the vector is a 0 vector. Positive V or negative V, the magnitude is still the same. They will have the same magnitude, but opposite direction. Of course, we're not talking about direction here. A number times a vector V is the magnitude of a number times vector V is absolute values of a number times the magnitude of the vector V. So there's a reason we use 2 bars instead of 1, because 1 bar for a number is absolute values, 2 bars is for a magnitude of a vector. Actually, when we get to a higher level, we just use 1 bar, and whenever we have the vector, we know that is going to be a magnitude. Whenever we have a number, we know that it's going to be in absolute values. But in a sense, they are the same thing. If the magnitude of a vector is 1, we call that a unit vector. Right. Now we go to an algebraic aspect of a vector. Now we did mention that a vector has no location, right? So now if it has no location, we will move so that the tail end will be at the origin, right? So in that case, if we move all the vectors so that the tail end is at the origin, then the vector we only need to specify where is the head of the vector, right? So in that case, the vector will be characterized by the head of the vector, assuming the endpoint is at the origin. Right, so that's what we call the position vector. So we have the initial point is at the origin. All of them will be at the origin. Therefore, the vector is characterized by the tail end. So we write the vector v is equal to AB. Once again, if we call this point is equal to the point A and B, right? Or sometimes we just say the point P has coordinate of A and B, or we can write equal to. But when we say the vector V equal to A and B, we will use the angular bracket to denote a vector as opposed to a point. A point we use parentheses, a vector we use angular bracket. But when we get to the higher level, we use the same notation. We use this notation when we go to the high level of math. We assume that a point is a vector is a point. And actually, they're the same because they have both of them have two components, A and B. So the point is a vector and the vector is a point. That is if vector is understood so that the initial point of the vector is at 0, 0 at the origin. Then the end point of the vector will be characterized the vector itself. So the end point of the vector is characterized by the vector. It's characterized the vector itself, right? So later on, a point is just a vector, and a vector is a point in a high level. Right. Now, suppose a vector V connect two points x1, x2, and x1, y1, and x2, y2. So we have 2 points. And notice the notation here. All of them are regular phase, no ball phase here. Then vector V is a vector P1, P2. When V is equal to the position vector V is P2 minus P1. So in general, we say vector V is equal to vector P1, P2. It is a vector, so there's an arrow on the top of it. Will be equal to the coordinate of the end, the head minus the tail. Right. So from P1 to P2, it's going to be P2 minus P1. Right. Final minus initial. The head minus the tail. Right. So keep this in mind. So if we have 2 points, subtract the end points, give us the vector, the end point, the final minus the initial, in that order. Right. Now, I did mention that the reason students get hung up with the concept of vector because it can be represented by too many different ways. Because that notation, or different of 2 points. And now it's another way using the component vectors. Right. Let I denote the unit vectors. What did we say about the unit vectors? Unit vector, once again, the length equal to 1. Magnitude is equal to 1. And the I is the direction, the unit vector along the positive x direction. And the J is also a unit vector in the positive y direction. So if we have a vector I, will be, so in that case we say the vector I is equal to the point 1 and 0 component of 1 and 0. So 1 on the x-axis and 0 on the y. So if we have the vector I in position vector, the end point at 0, 0, so that will be vector I, and that is vector j, and it also has to be a vector, so this should be a vector I, and this is a vector j. It's the bold face, and in that case we can represent a vector as a component to this. For example, let's say if we have a vector that is half of this and here, let's say if this is the vector v, we go half a unit on the right and then 1 unit up. Let's say if that is the vector, so go 1/2 unit on the right and 1 unit up. We can write the vector like that. We can also write the same vector as 1/2 times vector I plus 1 times vector j. Right. So the I component gives us the horizontal component, how much we go on the right. If it's negative, of course, it go to the left. And j is the vertical component. If it's positive, go up, negative, go down. It tells us how many units that we go up and or down. And we can write a vector geometrically in this form, but algebraically we can write in the angular bracket notation or IJ notation. Right. That. Next, when we write a vector in algebraic representation, either in angular bracket notation or IJ components, it will be a lot easier if we do the sum or the scalar multiplication. Right. Says that the sum of two vectors is the sum of the components. So if vector v has the component a1, b1, you can write a1, b1 in the angular bracket, or a1i, b1j. When we add them, we can just add the first component with the first component, the second component with the second component. The nice thing when we write like this in the ij, in the component vector, let's say a1 plus a2 times vector I plus b1, b2 times vector j. When we add them, we have a1i, a2i, b1j, b2j, and then we can group a1, b1, a1i plus b1j plus a2i plus b2j. Of course, that is vector v, and the other one is vector w. Right. Of course, we can work backward, and we just combine like terms, and that's what we have here. Right. V plus w is this, and then combine like terms. Those two have I put together, and those have j put together. So either we combine like terms with I is a common, or we can just write in terms of the angular bracket. So pretty much to add vectors, we add component wise. The first component with the first component, the second component with the second component. Subtract the same way. If we multiply the number to the vector, we multiply that number to every component of the vector. And finally, the magnitudes of the vector is given by the Pythagorean theorem. Of course, that makes sense, right? if the vector v is like that, which has two components, v1, v2, or we say a1, b1, then of course the magnitude of v is equal to square root of v1 square plus v2 square. So the square root of the square, the sum of the square of the components. So once again, adding the vectors, we add the vectors component by component. Multiply the number to a vector, multiply that number to every component of the vector, and the magnitude is given by Pythagorean theorem. Right. Now let's do this. Usually, if I have a choice, I will prefer the vector in the angular bracket notation as opposed to the IJ notation. So let's add vector v plus w plus the v, vector v 4 and 2 plus vector w 2 and negative 3. So by definition, when we add them, we just add the components. First with the first, second with the second. So we have 6 and negative 1. Like I said, I prefer to write vector in that notation. If we use a calculator, it's no big deal. We don't really need the calculator, but if we want to, it's second parentheses, we can enter the vector as the list of number. Pretty much a vector now we have two components. The first one is horizontal component, the second one is vertical component. When we add them, we can just add like that. Open parentheses, open the second parentheses, give us the bracket. It has two components. And then we just add component wise. And that's what we have. Now we have v minus 2w. So we have v is 4 and 2. Minus 2w. So we have 4 and 2. So just like all the operation, we multiply the 2 first. Just multiply the 2 down to negative. So we'll give us still subtract. 2 times 2 is 4. 2 times negative 3, negative 6. And now we combine them. 4 subtract 4, 2 subtract negative 6. And we have 0 and 8. Of course, if we want to do that, oh wait, this. See, 2 times. I mean subtract, right? Yeah, that's what we have. Of course, it's no big deal, but just want to do that. All right. The magnitude of vector v. Vector v, I just say the magnitude of vector v, two component 4 and 2, given by Pythagorean theorem of those two components. 4 square plus 2 square. 4 square is 16, 2 square is 4. That's square of 20. Square of 20 is like square root of 4 times 5. Square root of 4 is 2. Square root of 5 is still square root of 5. Right. Next, for any vector v, the unit vector u is a unit vector that has the same direction as v. So we say the unit vector u will be equal to the vector v divided by the magnitude of vector v. So this vector u will be in the same direction as vector v, but the magnitude is equal to 1. Right? So it is the unit vector, meaning the magnitude is equal to 1, and it has the same direction as v. Unit, meaning that the magnitude is equal to 1. And it has the same direction as v. Right, next, find the unit vector in the same direction as v. Now this is a typo, right? This should be the vector v. In that case, the unit vector in the direction of v is equal to vector v divided by the magnitude of the vector v. The vector v is 6 and negative 8. Right, because you can write that notation or you can write that notation, it doesn't matter. But the magnitude is what? 6 and negative 8. So we say 6 square plus negative 8 square. 6 square is 36, 8 square is 64, 36 and 64, that's 100. So 6 and negative 8. So we have 6 and negative 8 divided by 10. Because when we divide by a number, or just like multiply by the reciprocal, we multiply the reciprocal to all the component. Pretty much we just have 6 divided by 10 and 8 divided by 10. So we take each component divided by 10. Of course, we reduce that, we will have 3 over 5 and 4 over 5. So this is the unit vector. The length of this is 1. The direction of this vector will be the same as vector v. Right. And yet there's another representation of the vector. Now, if a vector represents a speed and direction of the object, it's called a velocity vector. Now, of course, it's whether it's a velocity vector or not, it's not important. What we say here is that the vector v will be characterized as two components, cosine of alpha and type alpha, where alpha is the angle. I should remember we have previous section where we have x, y, rectangular coordinate go to r and theta polar coordinates. Pretty much the same thing here. So if we have alpha and the magnitude of v, then we can represent the vector in this form. So this is r cosine theta, r sine theta for the polar coordinate. But in this case, it is for the vector. So pretty much we have v is equal to that. But just even forget about the physical interpretation. A vector can be represented in this form as well. The magnitude times cosine of the angle that make with the positive x-axis. And vector v, the magnitude of vector v times sine. So recall what we have earlier. A point in rectangular coordinate. This is rectangular coordinate. We can write as r cosine theta and r sine theta. This is x, this is y, right? And if we write the point as r and theta, that is in polar coordinate. So pretty much that's exactly what we have here. R is the magnitude of the vector, and alpha is the angle made with the positive x-axis. Right, let's look at this example. A ball is thrown with an initial speed of 30 miles per hour in the direction that makes 30 degrees with the positive x-axis. Express the vector v in terms of I and j. What is the initial speed? What is the initial speed of the horizontal direction and in the vertical direction? So simple enough. So initially the ball is thrown 30 degrees. So it's about that direction, 30 degree, marked with the positive x-axis. And the magnitude is 30 miles per hour. Right. Now, in terms of physics, when we say velocity vector, we mean velocity is a vector and represent the speed and direction. So speed we obtain as the magnitude. So we say velocity is a vector whose magnitude is the speed, and direction is still direction. Right. When we say we arrive in, let's say at the speed of 50 miles per hour, we didn't say in what direction. But if I say I will ride with the velocity of 50 miles per hour going east, that is the velocity. It has a magnitude, a speed component, and it has the direction in the east direction, for example, something like that. So if we want velocity, we need a magnitude, which is the speed, and a direction, still a direction. Right, this direction is 30 degree with the positive x-axis. Right, so we have that. Now, express the vector v in terms of I and component vector I and j. So first we need to decompose this into component of horizontal component and vertical component. Right, let's say we have the vector v. If we want to, we can say this is the v, the first component, the horizontal component, v2, the vertical component of the vector. Right. And then, of course, with that figures, this is also the y component. This is the x component. The y component, of course, it's going to be y is equal to r sine theta. So same thing here. We have v2, the vertical component, equal magnitude of v times sine of the angle. So it has the magnitude of 30 miles per hour times sine of 30. Sine of 30 is 1/2. It is 15. V1 is the magnitude of v times cosine of 30 degree. So we have 30 cosine of 30 degrees will be square root of 3 over 2. That cancel out, we have 15 and square root of 3. Of course, the unit is still miles per hour. Right. So we have the vertical component, the horizontal component. So in that case, we say the vector v will have two components, v1 and v2. Or we say v1 times the horizontal component I, and v2 vertical component on the vector j. Or we say 15 I and 15 square root of 3 j. Right. Initial speed in horizontal direction is 15 square root of 3, and the vertical speed in the vertical direction is 15. So horizontal direction, initial speed in horizontal direction, this is v1, and the initial speed in the vertical direction, that is v2. Right, let's go to another example here. Boeing 737 aircraft maintain a constant speed of 550 miles per hour headed due south. So it goes south, but because of the wind, if blow that direction, it will go a little bit to the right. The jet stream is 80 miles per hour in the northeastern direction. Express the velocity with respect to the air and the velocity actually when I type it, copy and paste, it didn't look right. Let me write this again. How confusing. Right, so what we have is the velocity relatively to the air and the velocity of the wind. Right, now velocity of the air, velocity of the airplane with respect to the air is equal to it just had its due south 550 miles. So due south, so going down 0 and 550 going south. Right, so let's just draw the vector here, because north is south west. If we go in south, we don't go any left or right, so that is 0 horizontal component, and the vertical component is negative 550, so that's going down. So that is the velocity of the aircraft with respect to the air. Now velocity of the wind is 80 miles per hour northeasterly. Well, that requires a little bit of work, and I'm going to write that here. Right. So we know that the vector, the jet stream northeast, so split right between north and east. There's a magnitude of 80 miles per hour. So in that case, we have to decompose in two components. Vertical component and horizontal component. Because it is split between north and east, that will be 45 degrees. So the vertical component, the magnitude of 80 miles per hour times sine of 45 degrees. Let's just get an approximation here, because I just want to get the number. So more, if it is in degree more, 80 times sine of 45. So 56.6. So that is the vertical component of, this is the velocity of the wind going that direction. And this is 80, the magnitude, times the cosine, because that's the horizontal component. Cosine 45 degrees is also the same as sine of 45 degrees. So this is also 56.6. So the wind will have two components. The horizontal component of 56.6, and the vertical component is also 56.6 positive. Right. Now, I'll find the velocity of the airplane with respect to the ground. So, even though it tried to go straight, but the wind will blow it away. So, with respect to the air, it will just go south. But with respect to the ground, even though it trying to go south, the wind will blow it, so it's not going to perfectly south anymore. So the velocity is going to be velocity with respect to the ground is equal to velocity of the airplane with respect to the air plus velocity of the wind. So we just add them. 0 minus 550 is 56.6 and 56.6, and that gives us 56.6 and 56.6 minus 550 okay, 56.6 minus 500 negative 443.4. Right. So that is the velocity with respect to the ground. So it's not going straight down, straight south anymore. It's just a little bit to the right, a little bit east. For the actual speed and the direction, where to get the speed would be the magnitude. So square root of the square of the component. Square root of 56.6 square plus 443.4 square, and that gives us 446.99. So actually, if we take the square root and we use this number and plus, never mind, we round this up anyway. So yeah, so that's about 447 miles per hour. So that is the speed. And the direction, well, how do we write the direction? Now if the vector that goes down negative 443.4 and go is 56.6, and what is that vector? So we can get this this angle. Remember from previous section, tangent is equal to y over x. So y component 443.4 over 56.6, and we take the inverse. It is in degree mode, so tangent inverse of negative 443.4 divided by 56.6. I will have negative 82.7 degree. Right. So that is negative 82.7 degrees. If it go clockwise, of course. If it counterclockwise, it will be positive 82.7. Bottom line is we need this angle. That angle would be 90 degrees minus that. Right? The magnitude of the angle is 82.7. The acute angle is 82.7. So 90 minus 82.7. One. Sorry. 90 minus 82.7255. Right, about 7.3. So why do we need that angle? Well, this is the angle from the south to the east side. So the direction, if we want to give, it's going to be south 7.3 degree on the east side. So we give the answer as a bearing. And the speed is 447 miles per hour. And direction will be that. Right. So pretty much, if we have the vector, we decompose into the two components. The vertical component is multiplied by sine. Horizontal component is the magnitude times cosine. And when we add them, we just add the components. So that's pretty much it. Right. Now, let's go to this example. Two movers require magnitudes of force of 250 pounds to push piano up a ramp of 20 degrees from horizontal, so inclined plane. How much does the piano weight? Assume that there's no friction between the piano and the plane. Right, so we have the inclined plane. And the angle made with the plane is 20 degrees. Here's the object. Of course, if the object, the weight will point directly down, right? Right. So the weight point down. And we don't know what is the weight of the object. Now, the key to do this one when you go to physics, do not decompose anything as horizontal and vertical component when we have the inclined plane. Decompose things in two directions, one of which is the inclined plane itself, and the other direction is 90 degrees to it. So in that case, I will decompose the weight into two components. The component that is parallel to the inclined plane, and the component that is perpendicular to the inclined plane. So decompose the weight into two components. Let the weight be capital W. Then we have the horizontal component not the horizontal component, the component parallel to the inclined plane. This is W1 and this is W2. Right, so we decompose the weight that is vertically going down into two components, one of which horizontal to the plane, one of which is perpendicular to the plane. Right, now if this is 20 degrees, this is also 20 degrees. Right. Now just focus on that triangle. Right, W1, and this is the magnitude of W, and the angle is 20 degrees, and this is W2. Right, now we decompose the weight into two components, W1 and W2. Right, now we're interested in W1. Now, what is W1? W1 is opposite to the 20 degrees angle. Right? So W1 is opposite to the angle. So the magnitude W. So all we say opposite over hypotenuse will give a sine of 20 degrees is equal to opposite W1, the component, divided by the magnitude W. So in that case, if we get W1, what do we have? So just magnitude of W times sine of 20 degrees. Right. And this should be negative if we talk about it going down. Right. Right. So the weight will have two components. The horizontal component, or I mean the component on parallel to the ram is that component. Now, if we want, in order for this one not to pull down, the force that we push up, we have to push the object up. So at least the piano will move up the ram. That force have to be at least equal to the weight, at least equal to W1. So this is the force that we have, is 350 pounds of force to push it up. It have to at least cancel out with this component. So we're going to make that equal to each other, and we say the weight times sine of 20 degrees have to be at least 350, have to be equal to 350 if we want to push it. And this is the maximum weight we can have. In reality, we have the force we push have to be more than the force due to the weight that's sliding down. So in that case, to get W, the weight of the piano, we just take 350 divided by the sine of 20 degrees. 350 divided by sine of 20 degrees. We get 1,023 pounds. So the piano cannot weigh more than that. If it's more than that, 350 pounds will not be enough to push it up the ramp. Right. So like I said, on this one, usually in physics, my advice is do not decompose its horizontal and vertical component. Just decompose that into two components, one of which is horizontal, one of which is parallel to the ramp, and one of which is vertical, one of which is perpendicular to the ramp, one horizontal and one vertical. And then we just draw a triangle out and then determine, well, this is opposite, so it's going to be sine hypotenuse times sine, and this is adjacent, so it will be the magnitude times the cosine of the 20 degrees. And not only that, W1 will be negative because this point in opposite direction, so it's negative. And W2 is also negative because the weight in general point down, which is negative. Right, so pretty much we just decompose the weight into two components, the horizontal component and, the weight pointing down decomposed into two components, one of which is the parallel to the inclined plane and one of which is perpendicular to the inclined plane. The parallel component must be cancelled out with the vertical component, with the force that we push up, so those two have to cancel each other out. So in that case we have the weight cannot be more than that. If the weight is more than that, we cannot push the piano up the ramp. Right. Before I finish the video, I realized that I made a mistake earlier. So just want to go back and just mistake in the notation. Of course, that doesn't make any sense. What we have is, of course, the magnitude of the vector, so please change that. This is on the previous page. Yeah, please change that to the magnitude of the vector. Yeah, it's just the notation. I know. Right, yeah, like I said, it's just the previous page. Right, so with that, I finished section 8.4. As always, thank you for watching and see you in another video in calculus.